So good evening. Welcome to the problem solving and doubt clarification session for the NPTEL online course on water and wastewater treatment. So we are in week 8 now, and this course is being taken by Professor Bhanu Prakash from IIT Roorkee, and I am one of the teaching assistant. I am Akash Saha. I am a PMRF scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. So we will quickly see the contents of this week 8. So we started with coagulation. Actually, we are in the ending stage of coagulation. So where we learnt about the alkalinity requirements and different types of alum salts, their operating regions, and some more about the ferric salts and their operating region. And then we moved into the rapid mixing, followed by the coagulation. So where we learnt about various organic coagulants, the jar test, how the test is being done, what are the optimum dose and at optimum pH, how to find out the coagulant, and the types of rapid mixing basin design, and the mean velocity gradient. And then we moved on to the flocculation. We learned about the mechanism, the types of flocculation basin, the design of the flocculant basin, and the flocculator pattern. And at last, we moved into the flocculate setting, that is the type 2 setting. What are the critical design parameters, and what are the primary design variable, and the inlet outlet hydraulic design consideration. So this was all about the contents of week 8. So I have some subjective and objective questions regarding this. So we will solve them one by one. So this is the first question. So it says that a chemical supplier reports the concentration of stock alum chemical as 9.58% as Al2O3 with a specific gravity of 1.32. So what will be the molarity of Al3 plus ions? So we have the concentration of the stock alum chemical, that is 9.58. So it is given as Al2O3, and the specific gravity is also given. So now we have to calculate the molarity or the moles per liter. So kindly try to solve this problem, then we'll see how to go about it. I'll wait for a minute. Okay, so I think we can look into the solution. So I'll solve the problem. So question number 1. So if you see the molecular weight of Al2O3, it is 2 into 27 plus 3 into 16. So it will be around 102 gram per mole. So this is the molecular weight, and the density or the it is given as 1.32 kg per liter. Specific gravity is given, so we can convert into the density 1.32 kg per liter. And so what will be my, so first we will find out the concentration of alum in the stock. So we have given the stock chemical. So concentration of alum in the stock as milligram per liter of Al2O3. So first we will find out this. So my C stock. So my C stock will be, so we are given 9.58%. So 9.58 by 100. So this is in percentage into the density 1.32 kilogram per liter, and from kilogram to gram it is 10 to the power 3 gram per kg. So if we do the calculation, we will get 126.456 gram per liter Al2O3. So this is the concentration of alum in the stock chemical. So we will just multiply the percentage into the density into the unit conversion. So we will get the concentration of Al2O3. So now we will find for Al3 plus. So what we will do, we will have to find out the molar concentration of Al3 plus in stock chemical or stock alum chemical. Stock alum chemical. So my concentration of Al3 plus will be, so whatever is my concentration of alum, this is my concentration of alum. Now 1 mole of Al2O3, as we have found out, has 102 gram of Al2O3. So Al2O3, the molar weight, so divide by the molar weight into, now per mole of Al2O3 we have 2 moles of Al3 plus. So per mole of Al2O3 we have 2 moles of Al3 plus. So it is nothing but 126.456 divided by 102 into 2. So this will be my final answer. So I will get the answers in moles per liter. So 2.479 moles per liter, or I can write 2.479 molar. So this is the concentration of Al3 plus in my stock chemical solution. Okay. So I hope it is understandable. So first we will calculate the concentration of alum in the stock chemical. So it is nothing but the percentage into the density and the unit conversion. So we'll get in gram per liter of Al2O3. So after finding it, now how much will be my molar concentration of Al3 plus? So we will, with the concentration, we will divide it by the molecular weight of Al2O3 into number of moles of Al3 plus per Al2O3. So that is 2. So once we do that, we will get the molar concentration of Al3 plus. Okay. I hope you have noted it down. So we'll move forward. If there is any questions, you can ask. So the correct answer is 2.479 molar. Okay. Now the next question, it says calculate the concentration of alum from the data in previous question. So now it is asking the uh, concentration of alum, but the unit will be gram per liter as Al2SO4 thrice dot 14H2O. So it is asking in terms of Al2SO4 thrice dot 14H2O. What is that? Is the hydrated formula of alum. So moving into this in the similar lines. So based on our previous question, whatever the answer we got, now we have to find out as gram per liter of the hydrated alum. Okay, so we'll see how to do this. So this is our second question. So first, the molecular weight of Al2O3. No, sorry, it is not Al2O3, it is Al2SO4 thrice dot 14H2O. So it will be 2 into 27 plus 3 into 32 plus 26 oxygen plus 28 hydrogen. So it will be 594 gram per mole. So now my C stock, like the last time we did, so now my C stock will be, we knew it is 126.456. So it is coming from the previous question, 126.456 gram per liter of Al2O3. So we will just find out the weighted average kind of thing. So it will be 594 gram per mole of alum per 102 gram per mole of Al2O3. So we will divide by the molecular weight of Al2O3 and multiply with the molecular weight of the hydrated alum. Okay, so this is nothing but 736.42 gram per liter of alum. So this will be my C stock. So this value we got it from the previous question, which is this one, this C stock as Al2O3. So we used it directly and multiplied with the molecular weight of alum divided by the molecular weight of the Al2O3. So in that way, we will find out the C stock in terms of alum. I hope it is clear. So the answer is 736.42 gram per liter of alum, Al2SO4 thrice dot 14H2O. Okay. So we'll move to the next problem. Okay. So now the question says, what happens when alum is mixed in water as a coagulant? So what happens when alum is mixed as a coagulant in water? So whether the pH will be decreased, pH will be increased, or there will be no pH change. So can you tell me the answer? A. So there will be a decrease in the pH. So that is correct. So why there will be a decrease in the pH? Because it will impart some acidity, as it will impart some H plus ions in the system. So when alum is added in water, it will give out some H plus ions. So that will consume the alkalinity, and hence the pH will be decreased. So that is how we will see in the further questions, like how it is imparting, how it is taking up alkalinity. I have a few numerical problems based on that. So we will see that. Okay. So next we will move to the next problem. So it says that if 12 ppm of alum dose is required for the treatment of water, then quantity of alum for treatment of 10 million liter water will be. So we are given the alum dose and we have to find out the quantity of alum for a particular discharge, that is 10 million liter. So we have to find out the quantity of alum in terms of kg. Dose is 12 ppm. So 12 ppm is equal to 12 milligram per liter. So the dose is 12 milligram per liter. And the discharge is also given 10 million liter, or we can say 10 million liter per day, 10 mld. So what will be my alum requirement in kgs per day? Okay, so we'll see how to solve this. So this is nothing. It's a very direct problem. So the dose is given as 12 ppm, or we can say 12 milligram per liter. So my alum required in kgs for 10 mld will be equal to 12 milligram per liter into 10 million liters. So 10 into 10 to the power 6. So liters per day into, now we will change milligram to kg. So 10 to the power minus 6 milligram per kg. So it is nothing but it will come as 120 kgs. So 12 milligram per liter into 10 mld into the unit conversion will give me 120 kgs. So directly we can get in terms of kgs. I hope you were able to access the week 7 video lecture, because I recorded it and put it in YouTube. Were you able to access it? So last week I recorded the week 7 lecture and put it in YouTube. Okay, no problem. Please check. It is there in YouTube. I think a similar problem was there. That's why I'm asking. Okay. So this is a direct question. Very simple. So 120 kgs. So, okay, the next problem. In water treatment, a jar test is performed to obtain the chlorine content of water, to obtain the optimal dose of coagulant, to find out the optimal time required for flocculation, to find optimum pH at which coagulation needs to be done. So which of the option is correct regarding jar test? So is it for chlorine content, or for optimal dose of coagulant, optimal time, and optimal pH? B. Yeah, so surely for optimal dose of the coagulant, we will use the jar test. So once we find out the optimal dose of the coagulant, we will also use the jar test to find out the optimal pH. So optimal pH is also required. So depending on my coagulant, whether it's alum or whether it's ferric chloride or any other bentonite clay, whatever we are using, not bentonite clay actually. So whatever kind of coagulant we are using for the process, so to find out the optimal pH, because the coagulation and flocculation will happen at a particular pH based on the coagulant. So both option B and option D are correct to find out the optimal dose and also to find out the optimal pH at which coagulation needs to be done. Okay, so both option B and D are correct. I hope it is clear. We'll move to the next problem. Okay, so the question says, what are the concentrations of iron and chloride in 3 molar FeCl3, that is ferric chloride solution respectively? So we have to find out the concentrations of iron and chloride. There are 4 options here and 3 molar ferric chloride is given. So for iron and chloride we have to find out the concentrations in molars. Option B, yes. So directly we can see, no need to calculate. So 1 Fa per FeCl3, so 3 into 1, so 3 molar Fe3 plus, and 3 Cl minus ions will come, so 3 into 3 9, so 9 molar Cl minus. So pretty direct and easy. So option B is correct. Next question. It says that tapered flocculation is more efficient when compared to conventional process of flocculation, as it promotes aggregation of smaller particles into larger aggregates to enhance their removal by gravity. So is it true, false, true when reactor size is large, or none of the above? False. Why do you think it is false? What will be the true?
No, no, no. Sorry, sorry. It's true.
It is true. It
Yeah.
is true. Can you tell me why do you think it is true? Why tapered flocculation is better than conventional? Any idea? So what actually happens is, in the case of conventional process of flocculation, the G value will be the same. So we govern the flocculation in terms of the value of G, that is the velocity gradient. So in terms of G. So when we have tapered flocculation, so we will move from a high value of G to a low value of G. Okay. So when there is a high value of G, the uh, particles that will be found will be small but dense. Okay. But when there will be a low value of G, the particles which will be formed will be large but lighter. So we want large and dense particles. So
Can you please repeat again?
okay, wait, I will make a note of it. So we can say the flocculation is basically governed by the G values. Okay, so conventional, in conventional, the G is same throughout. The G is same throughout, whereas in tapered, first we will have large G and then it will go to smaller G value. So when large G is there, the particles which will be formed will be smaller and dense. And when the G value is smaller, the particle will be larger but light. Okay, so lighter flux will be formed. So since we want a combination of this, we want denser particles and larger particles, denser and larger particles. So for
But
that,
while larger particles, if they are lighter, they are not going to settle, I suppose.
yeah, that's what I'm telling now. We want a combination of this dense and large. Okay, so large and dense it will be there. So it will accumulate properly, and with density it will fall down. So since we want a combination of that two, we will go for tapered flocculation instead of conventional, because conventional the G will be same throughout. So if the G is same throughout, either we will get small and dense or we will get large and light. So since we want a combination of these two, we will go for tapered. So that is the main idea behind it. Is it okay?
Right.
Ah, okay. Okay. So this was about this problem. So
What about option C? What about option
that
C?
is just to confuse. That doesn't matter. Whether the reactor size is large or small, that doesn't matter.
That has nothing to do with the exercise.
No, no, no. It is
Okay.
just depending on the value of G. It was given just to confuse.
Okay. Okay. Thank you.
So option A is correct. Okay, the next problem. So we have to match the following flocculation mechanisms with their characteristics. So we have three types of flocculation mechanism. One is at microscale, that is perikinetic. one is macro scale orthokinetic, and one is differential setting. So three characteristics are given, so we have to match them accordingly. So is it due to when particles have differential velocity, settling velocity, is it by Brownian motion or is it by relative motion of fluid? So we have to match the mechanism with their characteristics. Please try to guess the answer. Option D. Okay, we'll see. Yeah, option D is correct, because for microscale or perikinetic, it will be depending on the Brownian motion. Okay, so microscalar Brownian motion, depending on the thermal energy, it will be depending on. For macro scale, it is the particle size is much larger, so it will be depending on the relative motion of the fluid. And the third one, differential settling, it is due to the differential velocities. So directly we can say option D is correct. Sure. So we'll move to the next problem. Oh, again a numerical we have. So consider a coagulation treatment plant. The flow rate is 0.15 meter cube per second. The alum dosing is 22 milligram per liter. The influent suspended solids concentration is 30 milligram per liter. The effluent suspended solids is 15 milligram per liter. Now, when alum is mixed with water, the stoichiometric equation is also given. Al2SO4 thrice dot 14H2O gives 2 AlOH thrice plus 6H plus 3SO4 2 minus plus 8H2O. So we have to find out the amount of total dry sludge solids produced per day. So we have to find out the total dry solids. So we have two things here. In the coagulation treatment plant, we have alum. So alum is mixed with water. So since alum is mixed with water, it will give some aluminum hydroxide precipitates. So it will give some dry solids. And also there are some suspended solids that are removed with it. So the influent is 30 milligram per liter and the effluent is 15 milligram per liter. So from that also we can find out how much suspended solid is also removed as dry sludge. So totally how much is my dry sludge that is being removed, we have to find out. Okay, we will see how to solve this problem. So this is question number 9. So the flow is given as 0.15 meter cubes per second, or we can write 12,960 meter cube per day. So just I am changing it to meter cube per second per day. Okay. So we know that Al2SO4 thrice dot 14H2O is giving me 2AlOH thrice plus 6H plus 3SO4 2 minus plus 8H2O. So this is my equation. So the molecular weight of this alum will be 594 grams and the molecular weight of AlOH thrice is 78 grams. So these are my molecular weights. So it means that 594 grams alum will give me 78 grams of AlOH thrice sludge. Okay, so that means 1 gram of alum.
Isn't it 2 into 78?
Oh,
2 more into
sorry. Yes. Right. It is 2 into 70. Right. It is 2 into 70. So 2 into 78. So 1 gram will give 2 into 78 by 594 grams of ALOS sludge. So we have our so doses 22 milligram per liter alum. So it will be equal to 22 into 2 into 78 by 594 grams. So this will be equal to around 5.786 milligram per liter of sludge.
Is
So
this
this,
dose given in the question? 22 milligram per
yeah,
liter.
yeah, yeah. It is given in the question. This dose is given in the question. See, alum dosing as 22 milligram per liter. So this
Correct.
dose is
Okay.
given. So we found out the uh, sludge with respect to my alum. So this is due to my alum. Now suspended solids are also removed. So suspended solids removed is influent was 30 milligram per liter and effluent was 15 milligram per liter. So totally 15 milligram per liter of suspended solids is also removed. So suspended solid sludge will also remove. So my total dry sludge solids will be 15 plus 5.786, that is 20.786 milligram per liter. So this is my total dry sludge solids. Now it is given as milligram per liter. If we multiply with the inflow, that is my uh, 12,960 meter cube per day, we will get in terms of kg per day. So my total dry such solids per day in kgs. In kgs, we will get 27.6 milligram per liter. I can also write it as gram per meter cube. The units are same, into my 12,960 meter cube per day into now kg to grams, it will be kg by 1000 grams. So this is all about it. So we'll get 269.387 kg per day. So this is my total solids, total dry solids per kg per day, kg per day, that will be given. So what we did is, first, from the basic equation of this alum in water, we got how much of AlOH thrice is getting precipitated. So we found out to be 5.786 milligram per liter of sludge. Now some amount of suspended solids are also removed. So that is 15 milligram per liter of suspended solids. So total I got as 20 milligram per liter of solids. So if I want to find out in kg per day, I will just multiply with the inflow. I will just multiply with the inflow and I will get the kg per day dry solids per day. Okay. So this was about it. We'll move to the next problem. I hope it is understandable. So answer is 269.387 kg per day. Now the next problem. A flocculation chamber has 12-meter long, 0.25 meter wide paddles. Both paddles are supported parallel to the horizontal shaft. The shaft rotation speed n is 6 rotations per minute. Center line of the paddle from the shaft is 1.8 meter. Coefficient of drag is 1.8. The ratio of the velocity of the paddle with respect to water to the velocity of paddle from a fixed coordinate is k is equal to 0.75. So we have to find out the power consumption by the shaft. So this is basically the paddle design, for paddle design. So what will be my power consumption for the shaft? So we have a direct formula for the power given for the shaft. So we have P is equal to half CD rho A into V cube. So my V will be the velocity of the paddle with respect to water. So to find out the velocity of the paddle, we need some parameters like K, the shaft rotation speed, etc. And then we have the area, and also then we have to find out the power. Okay, so we'll see how to solve this problem. So problem number 10. So my power is given by P is equal to half CD. Rho is the density of water, AP is the area of paddle, and VP is the velocity of oil. So VPQ. So we have to find out all the parameters. So CD we know, CD is given as 1.8. Rho W also we know, 1000 kg per meter cube. Now AP, area of paddle, it was 12-meter long and 0.25 meter wide. So that is 3 meter square. So that is 3 meter square. AP is also known to us. Now the last thing is the VP. So my VP is the velocity of paddle with respect to water. So my VP will be equal to K times 2 pi Rn. So K is the coefficient. Coefficient is known, that is 0.75. It is given in the question that with respect to water, what is the velocity of paddle? That coefficient is 0.25. Then 2 into 22 by 7. Now R is the radius from the shaft. So that is 1.8 given in the question. And 6 revolutions per minute. So it will be 6 by 60. So my n value is 6 by 60. So this is the velocity of paddle. So we will get it as 0.8478 meter per second. So this will be my velocity of
N
paddle.
is number of, excuse me,
Sorry.
N is number of revolutions per second.
Yes, because we are finding out in meter per second.
Okay.
Okay. So my P value will be half into 1.8 into 1000 into uh, and now how many paddles are given? Okay, so basically there are two paddles. So my area will be, area per paddle was 3 meter square. So for two paddles it will be 3 into 2, and then the velocity cube 8478 cube. So my power will be equal to 3290.51 watts. So this will be my power, 3290.59 watts. Okay. I hope it is clear. So all the parameters CD, rho W, AP and VP we have found out, and we have just replaced it and we got the answer. So this K 2 pi Rn, this is important, and N is in uh, rotations per second. So the correct answer is 3290.59 watts. Move to the next problem. Consider a water treatment plant having Q in, Q influent as 12960 meter cube per day. The dynamic viscosity is 10 to the power minus 3 Newton second per meter square. The velocity gradient, that is the value of G, which we discussed, is 850 per second, and the tank is used to blend 35 milligram per liter of alum with a flow for a detention period of 2 minutes. So detention period is also given. The power input required for the mixing. So power input can be found out in two ways. Either we can find out with respect to the velocity gradient and the volume of my reactor, or you can find out the actual power in the shaft due to our paddle configuration. So here it is the power input with respect to my volume and the velocity gradient. So we have direct formula, power is equal to G square mu V. So once we substitute the formula, we will get the answer. We will note down the question. We'll see the solution now. We'll see the solution. So question number 11. So power input required for rapid mixing in terms of temporal mean velocity gradient. That is my G. So G is also called temporal mean velocity gradient. So P is equal to G square mu into V. So this is my equation. So mu is 10 to the power minus 3 Newton second per meter square, and G is also given 850 per second. Now we can write it as the discharge into the detention time, Q into T. So discharge is given 12960 meter cube per day into it is given as 2 minutes. So 2 I will change it into second days. So 24 into 60. Okay, days. So we'll get V as 18 meter cube. So my V is 18 meter cube. So now P will be 850 square into 10 to the power minus 3 into 80. So my P value will be 13005 watts. Okay, so 13005 watts. So this will be my power in terms of the temporal mean velocity gradient. I hope it is clear. We move to the next problem. A water treatment plant has a flow rate of 504 meter cube per hour. A particle of certain size has a settling velocity of 0.14 centimeter per second. The required plan area in meter square of the type 1 settling tank to remove 90% of the particles of this size is. So we have been given the flow rate and the particle settling velocity is also given. So we have to find out the area or the plan area for type 1 settling tank, for which only 90% of the particles are getting removed. Not 100%, only 90% are getting removed. We have solved these kind of problems during wastewater treatment design. So similar approach. We'll see how to solve this. So Q is given as 504 meter cube per hour. So we'll change everything in meter cube per second. So it is 0.14 meter cube per second. Now the settling velocity Vs is given as 0.14 centimeter per second. So it will be 0.0014 meter per second. So my plan area for 100% removal. So this is for 100% removal. So my plan area will be Q by Vs. So Q by Vs will be my plan area. It will be equal to 0.14 by 0.0014. So it will be 100 meter square. So 100 meter square is for 100%. So to remove 90% particles, my area 90% will be equal to 100 into 0.9. Directly we can get 100 into 0.9, so 90 meters square. Okay, so very simple. Plan area is equal to my Q by Vs. So this will be for 100% of removal, but we need only for 90% removal. So we'll multiply it with 0.9, and so we'll get 90 meters square. So direct answer. Okay, we'll move forward. So the answer is 90 meters square. So again, match the following type. So match the process with their primary design variables. So we have rapid mix design, flocculation design, and type 1 settling tank. And the design variables are critical settling velocity, detention time and mean velocity gradient, and the mixing intensity. So we have to find out the primary design variable for each of the design process. Please try to tell me the answer. Option A. No, I don't think so. It's a right answer. We'll see. So correct answer is option D. So for any rapid mix design, so rapid mix design will have two design variable. So one is the detention time T and the mean velocity G. So both T and G, like in the coagulation period, both T and G is important because we will mix it very rapidly. So my T will be very less and my G value is important. So rapid mix design, both. So the answer is B, detention time and mean velocity gradient. For my flocculation design, it's the mixing intensity. So based on my mixing intensity, the flocculation design will be governed. And for type 1 settling tank, we saw the critical settling velocity is important. That is the VS, critical settling velocity, or we can find out from the Stokes law or whatever. So that is important for my type 1 settling tank. So the correct option is option D. Okay. So this was about the 13th question. We'll move forward. Which one of the following types of settling phenomenon can be analyzed by sedimentation laws of Stokes and Newton? So direct question. So with the help of Stokes and Newton's law, what type of settling we can analyze? Discrete settling, flocculent settling, hindered settling, compression settling. Please tell the answer. Discrete settling. So directly we can say for discrete settling, which is governed by Stokes and Newton's law. Okay. Now one more numerical. A surface water flow of 15,000 meter cube per day is coagulated by adding 50 milligram of ferrous sulfate and an equivalent dose of lime. If lime is 87% pure, then the quantity of lime required. Okay, so how much lime requirement is there? Kg per day, we have to find out. Please note down this problem, we'll see the solution. So here instead of alum, it is coagulated with ferrous sulfate. So how much lime will be required? So we will solve this problem with the help of equivalence. So most of the problems we are solving directly with formula. So we'll see how to solve this in terms of equivalence. So question number 15. Uh, so whenever there is a reaction, so one equivalent of one chemical will react with the other one equivalent of the other part. So we can say one equivalent of FeSO4 reacts with one equivalent dose of lime. So what is one equivalent of FeSO4? It is nothing but, so the total molecular weight of FeSO4 is 278. So divide by 2. The combining carrying capacity is 2. So 2. So it is 139 grams. Similarly, one equivalent of lime. So it is lime is CaO. We can write 56. Again, the combining or carrying capacity is 2. So it is 56 by 2, 28 grams. Okay, so we can say that since one equivalent of FeSO4 react with one equivalent of lime, we can say 139 grams of FeSO4 will react with 28 gram of lime. So 1 gram FeSO4 will react with 28 by 139 gram of lime. So we have a dose of 50 milligram per liter FeSO4. So it will react with 50 into 28 by 139, that is equal to 10.07 milligram per liter of lime. Okay, so simple funda, one equivalent of anything will react with another one equivalent of the other chemical. So we first found out both the equivalent of FeSO4 and lime, and then by basic balancing we will find out the milligram per liter of lime. So now it is in milligram per liter. We have to find out in terms of kg per day. So we will just multiply it with the flow rate. So my flow rate is given as 15,000 meter cube per day, or I can write as 15 mmt. 15 mmt. So my lime consumption will be 10.07 milligram per liter into 15 into 10^6 liter per day divided by from milligram to kg. We are dividing by 10 to the power 6. Okay, so we'll get 151.07 kg per day. So this much of lime is required. But this much of lime is required if lime is 100% pure. 100% pure lime. But in our question, it is given as it is 87% pure lime only. So since it is only 80% pure lime, so for 87% pure lime, my lime consumption will be 151.05 divided by 0.87. That is 173.62 kg per day. So this will be my actual consumption because the purity is not 100%, it is only 87%. I hope it is clear. If you have any queries, you can ask me. This was the question. The answer is 173.62. Repeat. Okay. So it says that a surface water flow is there with Q is equal to 15,000 meter cube per day, and we are adding 50 milligram per liter of ferrous sulfate. So since we are adding 15 milligram per liter of ferrous sulfate, there will be a decrease in the alkalinity. As we know, when we add any coagulant, there is a decrease in the alkalinity. So to make up for that alkalinity, we are also adding an equivalent dose of lime. Okay, so it is asking like how much lime will be required if it is 87% pure. Okay, so what we did, we used a very simple funda. It is one equivalence of anything will react with one equivalence of any other thing. So one equivalence of FeSO4 is will be 278 by 2. So molecular weight of FeSO4 is 278 and the combining capacity is 2. So it is 139 grams per mole. Or it can say 139 gram per equivalence. 139 gram per equivalence. Similarly, for lime, it is 56 by 2 or 28 gram per equivalence. So, since one equivalence is reacting with one equivalence, we can write 139 gram of FeSO4 will react with 28 gram of lime. Okay. So, like that, for 50 milligram per liter of FeSO4, we found out that 10.07 milligram of lime is required. So now if we multiply it with the inflow, we will get the lime consumption if it is 100% pure. But since it is only 87% pure, we will divide it by 0.87 and we will get the final answer. Is there anything else? Okay. So simply we can find out the answer. Okay, so we'll move to the next problem. So now in this problem, whatever we have learnt about flocculation, all the theory will be utilized. So it's a complete problem. So it says that a water treatment plant is being designed to process 50,000 meter cube per day of water. So a water treatment plant is there. Now with the help of jar testing and some pilot plant analysis, it indicates that an alum dose of 40 milligram per liter is required with flocculation at a GT value of 4 into 10 to the power 4. So the GT value is also given because it is a design criteria for flocculation. So GT value is also given. So it produces optimal results at expected water temperature of 15 degrees Celsius. So the temperature is also given. So determine the monthly alum requirement. Now the flocculation basin dimension, if 3 cross flow horizontal paddles are used. So we have to also design the flocculation basin. So it is showing that 3 cross flow horizontal paddles should be there and the flocculator should have a maximum of 12 m meter wide and 5 meter deep. to connect it appropriately. So the dimensions are also given. We have to also find out the power requirement and the paddle configuration. So everything related to the flocculation design is there in this question. So step by step we will solve the problem and we will design each of the parameters. I will also draw the reactor so you can see how is the orientation of my flocculators, what is the distance, what is the dimensions, everything also I will draw. So like that we can see the complete problem. So alum dosage is also given, the GT value is also given, rest of the things we have to design, the power and the paddle configuration. Okay, you please take a screenshot of this question. We will see the solution now. Okay, so first is the monthly alum requirement. So question number 16. So first A part, monthly alum requirement. So we are given the dosage as 40 milligram per liter. So this is my dosage, which is also equal to 0.04 kg per meter cube. So just changing the dimension. So I'm just changing the dimension of 40 milligram per liter to 0.04 kg per meter cube. So how much monthly will be required? So monthly alum requirement will be 0.04 kg per meter cube is my dosage into the uh, flow rate, that is 50,000 meter cube per day into 30 days per month, into 30 days per month. So my monthly requirement will be 60,000 kg per month. Okay, so the dosage was given, dosage into the uh, discharge into the number of days in a month, we will get the monthly alum requirement. So this is my first part. Now second part will be my, I have to make the basin dimensions for my flocculation or my flocculator basin. What will be my dimension? So we will do how to solve it. So we know that in the question my GT value is given as 4 into 10 to the power 4. Okay, so GT value is given. So now if we want to find out the time, we have to assume some G value. So first we will just assume some G value. So assume an average G value as 30 per second. Okay, so 30 per second is my average G value that I am assuming. So my T will be equal to 4 into 10 to the power 4 divided by 30. Okay, so divided by 30, and if I 30 per second I can write, and to change it into minute, so 1 minute by 60 seconds. So my T value that I am getting is 22.22 minutes. So I got the time of my flocculation, 22.22 minutes. So it should be more or less than 30 minutes. So it is fine, 22.22 minutes. So this is my first part. Then I will find out the volume of my tank. So volume of the tank. So what will be my volume of the tank? V will be equal to Q into T. Flow rate into time will be my volume. So flow rate I know 50,000 meter cube per day into 22 minutes. Okay, and minute, since it is in day, so I will write 1 day by 1440 minutes. I'm just changing minutes into days. So whatever I will get, I will get V as 771.5 meter cube. So this is my volume. So I got the time, I got the volume also. Okay. Now it is also given. Now another thing is also given, that the tank will have 3 cross flow paddles. The tank should have 3 cross flow paddles. So my total length will be divided into 3 parts. Okay, 3 parts, or we can say 3 compartments. 3 compartments. So my total length will be divided into 3 compartments. So and so I will just make a small figure here. I will make a small figure here. Suppose this is my reactor. Okay, this is the water level. This is my water level. So I'm dividing into 3 parts. Dividing into 3 parts. So this is my first paddle. This is my second paddle. And this is my third paddle. So I've just, it is moving like this. I can just show the direction also. It is moving like this. So this depth, this depth I am assuming it as 5 meters. Suppose I am assuming this depth to be 5 meters. So so if this depth is assuming I am 5 meters, and each of the compartments I am assuming it to be a square. I am assuming each of my compartment to be a square. So this will also be 5 meter, this will also be 5 meter, and this will also be 5 meter. Okay. So my total length will become 15 meters. Fine. So each of my compartment I am assuming it to be a square. The depth I am assuming it to be 5 meters. So my total length will be equal to 15 meters. Fine. And my volume I know it is a 771.5 meter cube. So my volume, that is length into breadth, or I can write length into width into depth, is equal to 771.5 meter cube. So length I know 15 meters, width I have to find out, and depth also I know 5 meters. So this is 771.5 meter cube. So my width will be equal to 10.3. So now like this I can find out the uh, all my dimensions. So my length is equal to 15 meters, width is equal to 10.3 meters, and my depth is equal to 5 meters. So this is my whole configuration of my reactor. Okay. Now third is my power requirement. So how much power will be required? Power requirement. Now we assumed average G value to be 30 per second. In our previous assumption, we assumed that my average G value will be 30 per second. Now we know that in a flocculator, it's always better to give a tapered G value rather than single G value. Okay, so we have three compartments here. So instead of given same G value in all the compartments, we will give a high to low. So what we can do for average G value, for first compartment, we can give GS 40. Second, we can give GS 30. And third, we can give GS 20. Okay, so it will be tapered. And if we take the average, it will be 30 only. So our assumption also holds true. So for my first compartment will be equal to 40 per second. So these are all my G values. For my second compartment, it will be 30 per second. And for my third compartment, it will be 20 per second. So this I am doing for tapered flocculation. Okay, as I know, tapered flocculation is always better than conventional flocculation or single flocculation. So that's why I am doing this tapered flocculation. Okay, so now what will be my power requirement? I know my power requirement is G square V mu. Okay, so this is my power. So each of the for each of the compartments, I can find the power. So now at 15 degrees Celsius, my V mu value at 15 degrees Celsius is 1.139 into 10 to the power 3. So that's why the temperature was given, because for mu value we have to correct it. So this can find out from any table. So mu value is this. So my P1 for my first compartment will be equal to 40 square into total V was 771.5. So since three compartments are there, so by 3 into 1.139 into 10 to the power minus 3. So my P1 will be 468.7 Newton meter per second. And if I want to be in kilowatt, it will be 0.47 kilowatt. Okay, similarly P2 will be 30 square into 771.5 by 3 into 1.139 into natural minus 2. So it will be around 0.26 kilowatt. And the last one, P3, will be 20 square into 25, that is 771 by 3 will be 257.2 into 1.139 into 10 to the minus 2 minus 3, sorry, it is 10 to the minus 3. So it will be equal to 0.12 kilowatt. So like that we can get all the power requirement. Are you able to understand till here, or is there any confusion? It's a big problem, so that's why I'm taking some time. Please let me know if you have any confusion till now. Shall I go forward? Please give me some response. Shall I move forward, or shall I explain it once again? Okay, okay. I hope it is clear then. So we can move forward. So now my paddle configuration. So suppose this is my paddle. I will make a larger picture now. So this is my paddle, and if I see it from the other direction, it will look like this. Okay, so it will look like this. So now if we see this diagram, if we see this diagram, this total height was this total height was 5. So there is a little space here and there is a little space here. So generally more than zero point 0.3 meter is given more than zero point 0.3 meter of space is given in between. Okay, so suppose we are giving some 0.4 meter distance, 0.4 meter distance in both the sides. Okay, so 5 minus 0.4 minus 4 minus 0.4. So my total height of this paddle will be equal to 4.2 meter. So 5 minus 0.4 from the top, 0.4 from the bottom. So it will be 4.2 meter for the full paddle. Okay, and this will be my width of the paddle. This will be my width of the paddle. Fine. So this is the whole paddle diagram. Okay, so we'll see how to solve this. So in the question, it is given that each paddle wheel has 4 boards. So this one, two, three, 4. So each paddle wheel has 4 boards which are 2.5 meter long and W meter wide. So this is my width W and 2.5 meter long. It is given in the question. And there is 3 paddle wheels per compartment. And there are 3 paddle wheels per compartment. Okay. So now we have to find out this W width. So how we can find out? We know the power. We know the power for each compartment. Now power, we know it is equal to G square mu V. Otherwise, another formula is power is equal to half CD AP rho into VP cube. So this is another formula for power. Okay. So at 15 degrees Celsius, my rho value will be equal to 999.1 kg per meter cube. Now this VP we have to assume. VP is not given in the question. So we will assume VP to be equal to 0.5 meter per second. We will assume Vp to be equal to 0.5 meter per second, and my CD value will be equal to 1.8 because these are the general values. So these are my assumed values. I assumed my coefficient drag to be 1.8, Vp value to be 0.5. And what will be my AP? So my AP will be, we know there are 3 paddle wheels per compartment, 3 paddle wheels into 4 paddle boards are there. So 4 paddle boards are there per wheel into 2.5 is my length of the paddle into the width. So my AP will be equal to 30 W. So my AP will become 30 W. Okay. So now we know from our last problem that my P1, my first compartment, my P1 was equal to 468.7 Newton meter per second. This was my P1. So my P1 will be also equal to half into CD 1.8 AP is 30W into rho is 999.1 into zero point 0.5 cube. So this is also from another formula. So if we equate, so now we will equate 1 equal to 2. So we will get 467, 468.7 is equal to half into 1.8 into 30W into 991.1 into zero point 0.5 cube. So what I will get, W as equal to 0.14. Okay. So I will get W as 0.14 meter. Right? So first monthly alum requirement, we got the monthly alum requirement. Then we moved into the dimensions of my flocculator. Then we divided into three regions. We found out the power requirements for each of the region, and then by considering first compartment and the power required, we found out the width of my paddle board. So in that way, total design is done. Is there any problem with this question? You can ask me. Please let me know. If you want to go through again, I will tell. See, assumptions are required. If it is not given in the questions, then assumptions will be required. So that's why we have solved some small problems in the first. So in those small problems, whatever was given in the questions, we have assumed it here. So we can see the CD value 1.8. In my previous problem, it was there. VP value 0.5. So these are small assumptions that we have to make. If it is given in the question, we can directly take. If it is not given in the question, we have to assume it uh, by the general criteria, and then we have to design the problem. So this whole problem is a complete correction of all my problems that we have done today. So if you see all these equations, we are familiar. P is equal to G square V mu, then this paddle configuration. So if you want to completely design a flocculator, then this is the way. Okay. Maybe you can go through it once again in your free time from my YouTube channel, because I will upload this again. Is there any confusion in any of the part? Please let me know, then I will explain it. Like why we have done this, why we have done that, any confusion. This I hope this tapered tapered thing is clear, tapered flocculation is clear, because we assumed the G value to be 30 per second, and we know that tapered flocculation is better always than conventional flocculation. So for each of the compartments, we have given three different G values. But if you see the average G value, 40 plus 30 plus 20 by 3, it will be on 30 only. Okay. So once we get the G value, we can find out the power requirement for each of the compartment. And then once we get the power requirement, then we will come to the paddle configuration. So this is how a paddle looks, and there are four boards in each of the paddle wheel, and there are three paddle wheels per compartment. So like that, we will use this formula. CD and VP we have assumed, rho value we know for 15 degrees Celsius. So on the only thing remaining was my AP, area of paddle. So area of paddle was three 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 paddle wheels per compartment into four paddle wheels into 2.5 was my length, and width was W. So total area will be 30W. So then from the power requirement which we got from the earlier section, we use the same power here. and then equated it to the other power equation. So from that we will get the width of my problem. So this was the last problem today. Do you have any queries? Please let me know regarding all the problems that we solved today. Anything, any concerns? Solved examples of alkalinity. Okay. Actually, if you see in my previous class for week 7, there is a question on alkalinity. For alum alkalinity, one question is there. So you can see this problem, or even in the next class, I will solve one problem from alkalinity. Okay. So don't worry, I will solve a problem based on alkalinity. So we'll start the class with that alkalinity problem, and then for week 9, I will proceed. Anything else? Okay, thank you. If you have no more queries, you can leave the session. So we will have the next class again on 22nd March, same time, 7 to 9 p.m. on Friday. And this is my mail ID, saha19akash@gmail.com. So you can ping me if you have any queries. So if you don't have any more questions, you can leave the session. Saket or Kirti, do you have any queries?
Good evening, sir.
Yeah, good evening.
Actually, I wanted some problems on sedimentation, which is in circular section.
Okay, sedimentation. I think I have solved some problems based on settling rate and all, like with the help
Yes,
of,
sir.
yeah. Uh, I think you can go through my previous videos. I have solved some problems. If not, I will send it to you over mail. Okay,
Okay, sir.
no
Oh,
problem. I will send it to you. No problem.
sir, are you referring Metcalfe ID book?
I have Metcalf and AB, PV and Row, all the books I have.
Okay.
So, so you can check those books also. And for this water treatment, you can refer to MWH. So it's a very nice book, MWH. So that book will help you to solve all these problems. Okay.
Okay, thank you, sir.
Okay. Thank you. You can leave the session if you don't have any more. Saket, anything to be discussed? Are you there?